Thank you for the introduction. Yeah, my name is Tobias. I'm the CEO of Mostly AI, and excited to be here today. Good to see so many people interested in synthetic data. Quick question: who has worked with synthetic data before? Few. Okay, no, that's cool. I will. Before we dive into the Synthetic Data SDK, maybe I'll start briefly with a quick summary of what synthetic data is, the basics, basically, of synthetic data, because the term is also used quite differently today, and different people have different understanding of what synthetic data is. So when we talk about, or when I talk about synthetic data, most often I talk about AI-generated, sample-based synthetic data, which means you have some existing data, some production data, some original data that you use to train a machine learning model. That model learns the pattern, learns all the correlations, the insights, the distributions of the original data. And then with that trained model, it's possible to create a synthetic version of that data. Typically, the benefit of doing that is privacy. The synthetic data has all the statistical information of the original data, but none of the personal identifiable information. But there are other types of synthetic data. So sometimes people, when they talk about rule-based mock data, they also refer to synthetic data, and that's something like Faker, if you've worked with that, right? Just some dummy data that typically doesn't have any statistical meaning, but it can be useful for demo environments or software testing, those kind of things. And then there's a little bit of almost a hybrid, which is LLM-based AI generated mock data. And that has, I would say, probably in the past 2 years or so has become more popular. We won't talk about that today too much. We actually also have a software package that can do that. But that is where you actually don't have any data to begin with, so similar to the mock data case. But you then don't use a tool like Faker, but you use basically large language models and the pre-trained knowledge of the large language models to come up with new artificial data. And that also works surprisingly well. You get data that looks very realistic. I mean, you can try it with ChatGPT, with any kind of like AI assistant these days. Of course, the data doesn't have any statistical meaning, right? So you wouldn't use that kind of data to do any data science tasks, but you can use it for demo environments, you can use it for software testing, and those kind of things. And so we will focus today on AI-generated sample-based synthetic data. What are the use cases for that? What can you do with that? As I mentioned, the core benefit of that kind of synthetic data is privacy. It is fully anonymous data. So the use cases typically that we see in the industry are whenever there's challenges working or accessing data. Could be internally in your organization, especially large regulated or large organizations in regulated industries like banking, for example. Not everyone gets access to production data. But of course, it's also when you think about data sharing with third parties. So if, I don't know, you're a student, you're a researcher, you want to access some data from a large bank, for example, oftentimes it's not easy to do that, right? So the bank can create synthetic data and it can then share it with outsiders, partners, startups, vendors, and so forth. There are some other benefits with synthetic data, and we'll touch upon that as well. You can recreate the original data as closely as possible. That's kind of like the standard approach for privacy preservation. But you can also modify the data during the process. And we'll see that today with conditional generation and with fair synthetic data, where, for example, you can correct for biases that might be in your data. So you can actually get more diverse data, different data that you didn't have before. And that can help in your data science tasks. So much for the theory. And this is a tutorial, so we'll get hands-on very quickly. Yeah, question, please.
Very quick question. Very quickly, just you mentioned the two types of AI-generated data. What's the difference in the AI? So what do you mean AI without LLM? It's like traditional machine learning?
Yes, so for the AI-generated one, here we don't have, we're not using any pre-trained models. We're actually training models from scratch. And these are typically highly optimized models for the task at hand. So we'll see today using our SDK, it's a model architecture called tabular argon. It's a model architecture specifically optimized for tabular, for structured data, but it's not pre-trained. right? So basically, the SDK comes with the model architecture, doesn't have any information about the world or anything, and you then use your production data to train the model. Whereas with the LLM-based approach, you take the knowledge of the pre-trained large language model. So that's the difference there. Good question. Yeah, please feel free to interrupt anytime, obviously. We can do this as interactive as we want. So what we're going to talk today about is the Synthetic Data SDK. This is a open source, fully open source project, Apache v2 license, so it's fully permissive. You can do whatever you want. You can take it, you can put it in your products, you can fork it, you can develop on it. We released this beginning of this year in January, after actually, several years of working on the model architectures and all of the things behind it. So we've been around as a company for more than 8 years now, and for the better part, we're actually working on this. But we made the decision that it's time to bring more synthetic data to the world, and we believe that what we have here is actually quite powerful in terms of the accuracy that you can get for the data, in terms of the privacy guarantees, but also in terms of the scalability and just usability of the SDK. And that's why we open source this, right? So we want more people to work with synthetic data. We're always interested in getting feedback from the community. So if you use this, try this out, and you have some thoughts, ideas, definitely please let us know. You can also contribute to the project if you're interested. We're certainly open for that. So yeah, you can obviously go to GitHub. You can access the project there. You can give us a star if you like. And you also have all kinds of documentation, usage examples, and those kind of things to quickly get you started on the GitHub repo. We're not going to use that today because we actually have a notebook that I prepared that we're going to use. And I did share that already on the Discord channel. The notebook runs in Google Colab, and you can follow everything in Google Colab, and it's going to be fine. There's one caveat, it's going to be a little bit slow. So the standard resources that you get on Google Colab, especially for the third example that we're going to do, which is multi-table synthesization, running through that itself will probably going to take half an hour on Google Colab. Again, it's fine, it's going to work, but you might need to be a little bit patient. What I'm going to do is I'm actually going to run it locally on my MacBook here, which is surprisingly more powerful than the Google Colab instances that you get for free. And there, if you want to do that yourself, right, if you want to run it locally on your machine, or if you have some server somewhere where you want to run it, you will need to install the SDK. You will need to do a little bit of prep work. It is in the notebook. Given an example using UV, right? So I definitely recommend you use some Python environment management system. You can use Conda, you can use UV, whatever you want. If you want to use UV, there's all the instructions in the notebook how to do that. But I trust you probably will be able to use whatever environment manager you want to get that going. But eventually what you need is you need to install somehow mostly AI. Right? And we're going to use it in local mode today. Local mode means everything stays within the Python environment. No data ever leaves the Python environment. If you use the package in the remote or in the client way, it will actually connect to our instance, to app.mostly.ai, our publicly accessible service, and you will upload the data there. The synthesization will happen there, and you will get the results back. However, again, today we're going to do the local mode. So I'm not going to go into the setting up the Python environment and those kind of things. I will skip that, but again, if you want to do that, you can follow the instructions there, or again, use Conda, whatever you want. Or again, you just use the Google Colab directly in Google. All right, and we're going to go through 4 or 5 capabilities of the SDK. We'll actually start with the core capability. Super straightforward, super simple. We're just going to synthesize a data set. And so let's start. We'll import pandas, and we will initialize the SDK in local mode. And so we do that by calling local equals true. So what we now see here is the SDK in version 5.1.0. That's the latest as of, I think last week we released that. We typically release almost every week, definitely every 2 weeks, with some improvements, bug fixes, those kind of things. And it's running in local mode, right? So it's now connecting to my machine here. I actually see the resources that I have here on the machine, so 16 gigabytes of RAM and 10 CPUs. And so now this is running here, and I can connect via the notebook now to that instance, to the instance that's running of the SDK. And the first, I call it recap, because maybe some of you already have tried that before. We're just going to now synthesize the data set. We're using here the famous Titanic data set. Maybe you've used it before, maybe you've worked with it. There's a public repo on GitHub that we are maintaining. We have some couple of demo data sets. The Titanic one is also there. We're downloading it. We can preview the data set. And what we see here is, we have 1,300 rows. We have 8 variables, 8 columns. It's data about the passengers that survived the Titanic accident. And we have things like the gender, the age, what fare they paid, and other information. Actually, it's not only the ones that survived, but 0 means someone did not survive. So it's both. Good. And now what we're going to do is we're just going to call the SDK using mostly.train and providing the data as a data frame. And that's it. That's the first step of creating synthetic data. We need to what we call create a generator. A generator is now the model that has seen the original data, plus together with some metadata. But eventually what we're seeing here now, all the steps that are being performed by the SDK. So the data is being loaded, it's being analyzed, it's being encoded, and then there is the training of the model. Again, I mentioned before, this is what we call tabular argon, a model architecture that we developed. It's also open source. There's also a scientific paper around it if you're interested. It's an autoregressive model architecture, but it's highly optimized for first tabular data, and second also for CPUs, right? So here on my MacBook, I don't have any GPU. It works totally fine with 10 CPUs, and as you can see, it was quite fast. It's trained for 12 seconds, so quite quick, but it's also quite a small data set, right? It's only 1,300 rows, so not very large. What we see here is the training log. So what happens? So as the samples were fed into the model, we see this here. We see the epochs. We see the validation loss. As this is going down, the model learns more about the input data. And as I mentioned in the beginning, kind of like the model is trying to learn as much as possible about the input data. Now we have this generator, and we can now probe this generator using the mostly probe command and passing on the parameter size, so how much samples do we want. And this is it. This is now already synthetic data that was created in my Python notebook here. This looks structurally identical as the original data. We do see here some nans. That is because of the small model size and some privacy protection mechanisms that are coming into effect here. But typically, what I recommend is 5,000 rows of data or more. That's where things start to really make sense. Yes, it works now with here 1,300 rows of data. It also works if you only pass 200 rows of data, but then there's not so much for the models to learn. So the quality of the data is not going to be that great. But anyway, we very quickly generated here now 10 samples. We can say, okay, let's create maybe 20. Now we get 20. It's super fast. It's super quick, right? So the inference phase of the model architecture is also very fast, runs on CPUs, and this can be thousands of variables. This can be very wide data. This can be also millions of rows. Then it does take longer, but we have customers that run this with 1,000 variables and tens of millions of rows of data. And as you notice, so let's run this here again. This is always different, right? So we're sampling, so we're kind of probing the trained model, and it's kind of like what we call a random draw process. So the model has kind of like all the statistical information about the, in this case, Titanic data, and then we're asking the model, okay, give us 10 passengers, give us 20 passengers. And so in this random drawing process, it's a statistical process. That's why every time I'm probing here the generator, the data looks different, right? And that is meant to be like that. That is a feature. What I can also use is I can use the mostly generate command, using the generator and just passing the generator G to actually create a full synthetic data set. At the end of the day, it's very similar to probing, but what you will get is basically now a data frame as a result that you can then also show. And this here, so this synthetic data set then doesn't change, right? So once I've now created that, it always stays like this. Yes, please.
Can you say something about the guarantees on the distributions?
Yes, great question. So yeah, so the question was, can we say something about the distributions? And that is exactly what we're going to show next here. This is what we call the data model report. So using the reports function here, displaying true means we're just going to display this here in the notebook itself. You can also download this as a HTML file. This is a way for you to quickly analyze and see, okay, how well actually did the generator learn everything about the original data. What we're doing here is we're comparing a small holdout data set from the original data with a small synthetic sample, and we're comparing, okay, how similar, how different are those data sets. And so let's look at some of the data here. So for example, we have here the univariate distributions. So we had, I believe we had 8 variables. For example, here we have the age variable. So we see that apparently on the Titanic, we had passengers who were basically very young, 1-2 years old, and the oldest passengers were 80 or so. The gray line represents the distribution of the original data. The green line represents the distribution of the synthetic data. And so we're binning this here. On the right side, you see this here. We're binning this into 10 bins, and then we're looking at basically just the distance, and then we calculate this overall accuracy. In this case, it's 95.6%. Just by looking at this, yeah, it reflects the age distribution quite well. It's not perfect. There's a little bit, also highlighted here in red, a little bit of differences there. So 95.6 is not bad. We have higher variable values. For example, here we have 99%, we have 97.2% for sex. So this is a way to now assess basically the individual variables and the distributions of the individual variables. But what we're also doing is we're also looking at the bivariate distributions. So for example, what can we say here? What's interesting? Something we've survived, maybe. Yeah, maybe here. Age and fare. So we see here, okay, we have the different fares, and we have the different ages of individuals. This is kind of like the distribution, apparently, for, higher fares here if you were older. That kind of like is true also in the synthetic data, right? So we're looking here then in the synthetic data at the same bivariate distribution. We're also doing this on a trivariate level, so correlations of higher order. And yeah, you could do this also on a even higher dimensional correlational space, but of course it gets computationally very expensive. We're not displaying the trivariate ones because that would also be a little more difficult, but we're calculating it. And so what you see here then basically is what we call our accuracy metric. So basically taking the average of the univariate accuracy, the bivariate and the trivariate, you get this overall accuracy score. And that is a very quick way for you to assess, okay, is the data good or not? Typically, if you have larger data sets, you can get to 95, 97, 98% of accuracy, and that is a very good indication that the data of the quality is already very good. Here we have 91.3%. Yeah, it's a small data set. It's only 1,300 rows, not very large. There's some other metrics here. I'm not going to go into all the details there because it does get quite complex. But we have some similarity plots here. We have some distance metrics. These are interesting if you look at it from a privacy perspective. And then we have some more privacy metrics up here, the distances and so forth. But yeah, if you're interested in that, the mostly QA package, which is part of the SDK, it's also open source. You can also, and we'll see it actually later, you can use it directly, and there's an extensive documentation how everything is calculated and what it means. But at the end of the day, and also to answer your question, yes, you can quickly assess the quality of the synthetic data.
Just a very quick question. So identical matches means like identical in the original data set?
Yeah, so good question. Question around identical matches. So identical matches is a very interesting topic. So what we're actually doing is we're comparing identical matches within the original data and within the synthetic data. And comparing, is the share the same? What does it mean? So if I have a data set, for example, where I only have age and gender, and I have a population of hundreds or thousands of people, there will be identical matches, right? There will be someone like me, I don't know, male, 43 years old. Yeah, there are going to be several of that. And so it is just natural to have identical matches in even original data, by just comparing the data itself. In the synthetic data, you want to have the same share of identical matches. You don't want to have more than what you see in the original data. And so if you think of a more complex data set, something with, let's say, I don't know, 50 variables, there's going to be very little identical matches in the original data, and you should see almost no identical matches then in the synthetic data, right? So you want to see basically this number here, 11.7%, needs to be smaller than the 13.5. This is in the original data, this is in the synthetic data, so this is fine.
That's across all of the columns, right?
Yes.
So like if you would have an email in there, you probably wouldn't want to have any.
Yeah, so for example, if you have some direct identifiers like email address or social security number, I would recommend taking that out in the pre-processing step. Typically, you don't get a lot of statistical information from an email address anyway, right? So what are you going to do with it? But I would take it out. The only comment there on identical matches is because sometimes in some of our I don't know, competitors or other players in the market, they look at identical matches like, okay, is there an identical match between the original data and the synthetic data? So did the generator create something that one-to-one matches the original data? And then they say, oh, this is not good. From a strict privacy perspective, again, if I have a data set that only has gender and male, yes, there will be male 43 in the original data, there will be male 43 in the synthetic data, as long as there are enough male 43s in the original data, and it's not a privacy violation. It's a little bit abstract, and you need to wrap your head around it. But actually then removing identical matches from the synthetic data would be something that harms privacy, would not be good. So yes, if you think about a more complex example, like, I don't know, a banking customer with 50 variables, the chances are super low that the generator will create exactly that one customer, but it could happen, right? It's a statistical process and it could happen. Would that mean that this would be a privacy violation? No. As long as everything has been done properly, that's just, a random match. And so we would not advise to remove that. I know in practice some people would still remove that because they say, okay, well, it's difficult to explain that this was just randomly generated and it's not the actual person that we just took and put into the synthetic data. Say again?
So the main motivation would be you don't want to remove the randomness from your randomly generated.
Right, exactly. You don't want to remove the randomness, right? Because that would be an intervention and you would remove that. And we have a full blog post around that. It's called the Swiss cheese. Let's see if Google finds that. By removing identical matches in synthetic data actually risks privacy, and we take this analogy where I say, okay, if you look at a space like this, you removed some data points, and it's like, okay, what kind of data points did you remove? Well, you actually just removed the identical matches, and then, oh yeah, it's obvious. Okay, maybe you should not remove those data points. But that's, I would say, already a quite sophisticated privacy discussion to have when using synthetic data or the SDK. Yes?
Sorry, bringing you back to my previous question. Do you have any guarantees on the accuracy, like theoretical lower bounds or something like that?
Yeah, guarantees on the accuracy. So you see here in the light gray the theoretically maximum achievable accuracy. So you cannot get above that. So even if you take an original data set, right, let's say you have 1 million records of something, and you take a sample, I don't know, 100,000 or so, and then you compare that to the remaining 900,000, you will not get 100%, right? So the theoretical maximum accuracy is what's shown there. Okay, and so last step here, and we're now again just in the happy path of using the Synthetic Data SDK. I can export the generator using the export to file function. And then here, basically now my generator is here then as a zip archive exported. Why would I want to do that? Well, because I could then take it and import it somewhere else. So for example, maybe you have access to a super sensitive environment somewhere, you know, working somewhere, and it's like, you get access to some data. Yeah, you can create a generator. You can take that zip archive and then you can take it out and put it somewhere else. The generator itself is privacy preserving, right? So then the only data that you can generate is synthetic data. It's not the original data anymore. And that would be a way to, for example, take data from a super secure environment into something else. All right, so yeah, we're gonna cover now 4 topics that are a little more advanced. Differential privacy, that's where we start. So I will actually start doing it because it will take some time to run everything, and then I will explain differential privacy while we're doing this. So we're importing a couple more libraries here. We're initializing the SDK again, or we actually don't have to because it already is, was initialized. We're now downloading the adult income dataset. It's also quite a famous census dataset, US population, about 50,000 rows of data, I think from the 1990s. If you look at the first couple of rows here, basically social demographic information, marriage status, age, those kind of things. Quite a popular dataset. And there's one column here, the income column, that actually shows if a person at that point in time made more or less than $50,000. And that's a nice label you can use to train machine learning models. And so what we're going to do now is we're actually going to train 3 generators. One without differential privacy, one with a strong differential privacy guarantee, and one with a low or weak differential privacy guarantee. What we're now seeing here is an advanced way of configuring the SDK and configuring the generator. We have here, for example, the maximum training time. So training time is kind of like how long the model trains. Typically, the longer it trains, the better the quality of the data will be. I'm limiting this here now to 2.5 minutes, because otherwise it will take too long. And then we have here we have 2 parameters for differential privacy. If we turn it on, and that's epsilon and delta. And we'll get to that in a second. And we're just then basically calling 3 times these 3 configurations. So we have one configuration with an epsilon of 1.55, and with one configuration with an epsilon of 4.0. We're now kicking off the first initial training, no differential privacy. If you just look here in this column here, validation loss is what we saw before. The model is now training away. And so, quick question, who knows what differential privacy is? Good. Then, very high level intro to differential privacy, and I'm not using anything fancy, I'm just using Wikipedia, which actually I think does a pretty good job here. Differential privacy, it is a mathematical concept or framework for privacy. So if you're looking for guarantees, mathematical guarantees, how private or how anonymous something is, you want to look at differential privacy. It was introduced in 2006 by Cynthia Dwork from Microsoft, and it has since then probably become the standard for quantifying privacy risks or the level of privacy that you can guarantee. And the core idea is shown here. So if you have some database, and it's here D1 and D2, and there is some analyses that you're doing on that database, what you want to have basically with differential privacy in place is that the output of that analysis on that database, so answer A, should more or less be equal to answer B, independent of Joe's data here being removed or not. Right, so if you add someone to a data set, it shouldn't matter. Right? The one person shouldn't make any difference. So Joe was there, Joe was not there, doesn't matter. The answer is always A, which is more or less B. And so how indistinguishable those outputs are, that is what is quantified here, bounded by this parameter, what's called epsilon. The lower the epsilon, the higher the privacy guarantees. And researchers say that, an epsilon below 1, that's the best, or 1 or below is the best. In practice, oftentimes companies, and Apple, for example, is using differential privacy is like 10 or higher. it is a mathematical concept, right? Once you have something that is created differentially private, you can say, yes, here's the epsilon. This is the kind of like mathematical guarantee that you get. So much from a super high level. But of course, there's more to it if you're interested. You can definitely dive deeper there. So we now trained here a generator where we defined epsilon 1.55. And what we see here now is this column here where it says now differential privacy, epsilon and delta. Delta we can forget for the time being. It's just an kind of like additional information, but important here is the epsilon. So we defined a maximum of 1.55, and what happened is after the first epoch, already the epsilon was 1.4. It then grew to 1.51, and then it grew to 1.6. So as the training progresses, epsilon increases. And why is that? Well, epsilon, the way it's done, is also typically just injecting some noise. Injecting some noise into the analysis or into the data, but it basically makes the data quality worse. The more and more we train, the better the data quality gets. So kind of like with differential privacy in place, we have to stop. We have to stop the training so the data isn't so good. And we'll see actually, yeah, it lowers the quality of the data. But in this case, we defined 1.55 as the maximum epsilon, which means we're using this epoch here, the first one, which has an epsilon of 1.51. That's now the result, basically, of that training. And here on the second one, we actually now still see the training in place, happening here in real time. So here, differential privacy has now already grown from 1.91 to all the way to 2.23. Here we defined the maximum epsilon that we want to accept at 4.0. So it will continue to train. However, we also put in the training time constraint to 2.5 minutes. So it will stop after 2.5 minutes anyway, which means we'll probably stop because of the timing constraint and not because of hitting the 4.0 epsilon constraint. So it has been training for almost 2 minutes already. In 30 seconds or so, it will stop. And so differential privacy, if you ever need to create data where you somehow need to, I don't know, to a regulator, to some auditor, to someone need to prove mathematically, yes, there is a mathematical guarantee that this data is fully anonymous, you probably want to turn this on. And then you can say, okay, yes, this generator was trained, the epsilon that I got was, I don't know, 1.5, 2, 4, whatever, and that is then there, that is set kind of in stone. In practice, honestly, we don't use it all the time, because why? It makes training longer, it takes longer to train, it reduces the data quality, we'll see that in a second, and we are confident that our data is fully anonymous even without differential privacy. So in this case now it stopped at 2.72 epsilon, right? So that was before we got to the 4, but now we can see, okay, what's the impact of that? So we can now generate synthetic datasets, and we'll do that. We'll create 3 synthetic datasets. And also here, something if you ever want to go into the details of the generation step here, there you can also pass a configuration parameter. And here, for example, what we're saying is enable data report false. So you saw the chart before, right? The report, the data quality report. If we say false, we're not creating that, and that saves a little bit of time. So 3 datasets were created, and now we can actually visualize a distribution. We can visualize the distribution of the age variable. So what do we see here? And we see in blue the original data, right? And this is the distribution. Again, this is the adult US income data set. So we have people from 14 to 90 plus. That's the distribution. We then trained one model without differential privacy, and that's where the orange line is, right? And so we see, yeah, it matches very closely. There's a little bit of a dip here, but it matches very closely the real data set, and that's what we wanted, right? Then we trained 2 models with differential privacy on. We have differential privacy light, right, where we had eventually had the maximum bound at 4, but it stopped at 2.7 or something, if I recall correctly. 2.72. And we see the data is a little bit more distorted. It's not as close anymore. So the data quality got worse. And then we had the one generator with the DP strong 1.55, and what we see is the data even got worse, right? It's like almost like a uniform distribution at this point in time. And so this is the impact of differential privacy. Data quality will go down, and we can also quantify this using our QA, and now we're using here mostly QA, the package for quality assurance, to directly get the output for the univariate, the bivariate, and the trivariate accuracies that we saw before. And what we'll find, and this takes a little bit to calculate here in the background, is, again, the stronger the differential privacy guarantees, the lower the epsilon, the worse the data quality got. Again, something to keep in mind whenever you want to work with differential privacy. It takes longer to train, and it reduces data quality. But yes, you get a mathematical guarantee for privacy. So if that is important to you, it's something you might want to do. So here we have the results. The baseline generator without differential privacy got an overall accuracy of 97%. With the light differential privacy, we got to 92%, so just a little bit worse. But with the strong differential privacy guarantees, we got to 70%, so significantly worse data quality. All right. The next thing we're looking at is what we call question.
Thank you. For me, in the training with the, how did you call this, the light differential privacy, where epsilon was 4, for me it got only to 1.9.
Yeah,
Can you explain this?
Good point. So it depends on the compute power that you're now putting in there, right? So as I said, we're limiting by time, and we're limiting by the epsilon value. If you have stronger compute, you can actually crunch more data in the same amount of time, which means you can probably get to higher data quality, but also a higher epsilon. And I think on Google Colab, yeah, the difference between DB Lite and differential privacy strong is actually almost not there. So that's one of the reasons I'm also showing this here on my laptop. But yeah, that will depend on your machine. Okay, conditional generation. Conditional generation is where we actually start modifying the synthetic data, right? So what we now did before, right, and especially in the baseline case, we're just recreating the original data as closely as possible. Let's now move into actually modifying the data. So I'm again loading the adult data set just for completeness here. I'm training a new generator. We could have used the baseline generator from before, but just we have everything in order. This time I'm limiting the training time to 1 minute, not to 2.5 minutes, which effectively means the data is not going to be as good, but it's still going to be fine. And then what we're going to do is we're going to use that generator again to create a baseline synthetic data set. And then we're going to create what's called a seed data set that we'll use to create another synthetic data set. So this will take another 30 seconds or so. If there are any questions in the meantime, or if you want to catch up with your notebook, you get 30 seconds. Yes.
How would you recommend, I guess, creating a large volume of synthetic data and maybe perhaps trying to train or create the generator with a smaller volume? Is that possible?
So you have a large data set and you want to create a small data set?
Other way around.
The other way around, yes. Yes, that's possible. Once you have a trained generator, let's say you trained on 5,000 rows of data. Once you have a trained generator, you can create as much data as you want. You can also then create 5 million rows of data. Of course, the generator is not able to invent something that it hasn't seen before, but yeah, you will create more data.
Okay, thanks.
So it's a way to upsample data, yeah. All right, now we're creating this baseline synthetic data set like we did before, nothing crazy there. But now let's look at this here, this seed data frame. So conditional generation, the way it works is I have a trained generator, but then I also provide what we call a seed data frame, which describes certain characteristics of the data set that I want to see. So in this case, what we're doing here, we're actually providing an input on the sex variable, and we're actually saying, okay, we want to have exactly 50% male and 50% females. And this is just, using here this simple function here. We could also define other things. We could say, okay, I also want a 50-50 split between male and females, and I only want to have, I don't know, 25-year-olds or whatever, right? So you can define what you want, and this is going to be fixed. Everything else will be generated synthetically. So now, creating here is a seeded synthetic data set. What I'm doing is I'm passing here as a seed this data frame. So this is what I need to do. And then this kind of constraint is going to be applied in the synthetic data generation process. Still very fast, so that didn't change. But if I now compare the distribution of that sex variable, we see here in the real data set, we had about 65% males and about 35% females. In the baseline synthetic, that's more or less the same. But in the seeded data set, where we defined 50-50, that's exactly the case. We have 50% males, 50% females, because this variable, sex, was just taken basically from seed frame. Everything else was generated synthetically. And so that means that, for example, if we now also look at some of the other variables, if we now look at the hours worked, there will be some changes, right? Because we're almost simulating what would the US population look like if there was a perfect balance between female and males 50-50. And so in this case, we have in the original data set, we have the average work time per week at 40.4. On the baseline, it was very similar, 40.55. But in the seeded data set, we only get 39.3. Why is that? Well, because, at least back then, maybe still today, females on average are working not as much hours as males are, right? More part-time employment and those kind of things. So now that we lifted the share of females to 50%, as a consequence, the average work per hour, the average hours worked per week also went down. And all the other variables were also affected, right? So it's kind of like almost like a way to simulate data. You can simulate your customer base. You can say, okay, what would happen if we had a larger share of, I don't know, young customers or people living in certain zip codes and all those kind of things. It's quite a convenient way to do that. Cool. So, any questions around conditional generation? Otherwise, we'll move on to multi-table synthesis. Yeah, so far what we've been doing was single tables, right? A single data frame, quite straightforward. Data that is, probably good enough, or certainly good enough for some, data science use cases. You can train machine learning models. You could train an income prediction model, for example, on the Census data set, or a survival predictor on the Titanic data set. But oftentimes you don't only have one data frame, but you have multiple, and you maybe have a full relational database. So it is also possible using the SDK to actually do that, synthesizing multi-tables. So we're just going to initialize the SDK again, and we're going to download here a data set. Maybe you know it, maybe not. It's called the Burka data set. It's from a Czech bank in the 90s, and a guy named Burka actually made that publicly available on the internet back then. It's actual data, and it's one of the rare multi-table data sets out there. There are not many actual production data, multi-table data sets out there that you will find on the internet, but this is kind of like information from a bank. Customers, accounts, transactions, loans, credit cards, I believe, and it's like 7 or 8 tables. And again, it's also part of the public demo data repo that we have. And now what we're going to do is first just visualize those tables. These are the 8 tables and how they link together. So we have here for example, the account table and the client table. These are linked via a disposition table. The disposition table also has a link to the card table, and then the account also has the loans, the transactions, and the orders. So that's all coming to the account with a primary key foreign key relationship. And so we need that information now, and that I need to know when I use the SDK like this, because I need to configure those primary foreign key relationships now in the SDK, in the configuration. And this is how it works. So for example, I have here the clients table. In this case, there's only the primary key that I'm configuring as the client ID. But then here, for example, I have this disposition table, which is kind of like this table to have this end-to-end relationship. And there I say, okay, the foreign keys are 2. The account ID is referencing to the account table, and the client ID is referencing to the client table. What you will notice here is what is called context. Is context true or false? That's something specifically that you need to know. Why? Because the way the SDK works, you can only have context relationships between two tables. So here account disposition has the context relationship, but then here this other relationship between disposition and client cannot be context anymore. This can only be a non-context relationship. What does it mean in practice? It means in practice that the SDK, the model, will try to better learn the correlation between account disposition and card, for example, than between client disposition and account. So it depends a little bit on what you want to model. If you have just a simple, I don't know, star schema, for example, you don't have to worry about it. But if your relational table or if your relational model gets more complex, those are some of the specifics that you need to start thinking about how you model this. So, and again, with 7, 8 tables, it already gets a little long, right, the whole configuration. By the way, you don't have to necessarily do all this yourself. You can use ChatGPT, point them to the documentation and say like, hey, help me create that code. And that's actually what I did. It's pretty straightforward. I would say, and typically our recommendation is like up to like 15, 20 tables or so. This works. Beyond that, it just gets too complex, and the SDK is not able to capture all the information and correlations across those tables. So if you have, let's say, I don't know, if someone in your organization says, hey, I have an Oracle database with 1,000 tables, I want to have a synthetic version, yeah, that's probably not going to work out of the box. So, but what's happening now is in this multi-table synthesis, basically as we saw before, right, we're training models, we're doing all the steps that's necessary for that, right? We're pulling the data, we're analyzing the data, we're encoding the data, we're training the models. But we're not doing this once, but we're doing this multiple times. And under the hood, actually, we're using different model architectures. So for the tables that are kind of like independent or child tables in this case, for example, loan, order, transactions, we're using the model architecture that we saw before. But for some of the linked tables, we're using a different model architecture that's retaining temporal information, it's retaining information or correlations across tables. But again, you don't have to worry about it as a user. That's happening under the hood. At the end of the day, what the impact is that you will feel is it's going to take a little longer, right? Because we're not training multiple models. And especially if you're running this on Google Colab, this is going to take, I think, 18 minutes in order to complete. So that's going to take a little bit, especially here the transaction table, which is a little bit larger. Right, so while we're waiting for this to complete, what are the use cases here? Oftentimes it's for, data testing, or sorry, software testing, QA, where you have multiple tables, and someone says, okay, I want a synthetic representation of that. If you have data science use cases, and you at the end have a feature table that's kind of flat anyway, I typically recommend them just to take the feature table, the feature engineered table, and to synthesize that instead of actually going to the raw data. But it depends a little bit, right? And yeah, you can try one way or the other. But again, with multi-table, there will be limitations in terms of the complexity of how many tables you can have.
Maybe 2 years. There's a question online.
Yes.
Greg is asking, he's working on a churn data set with 5,000 customers, and he's asking to get a better understanding why he should use a synthetic data generator if then he has synthetic data for maybe 50,000 customers. What is the use case to create the synthetic data? For example, in this case, Greg is asking his churn data set.
Yeah, good question. So, yeah, I mean, so as I mentioned in the beginning, right? So I would say the core use cases are around privacy, right? So if Greg was not able to get actually the churn data because for privacy restrictions, if you're able to work with production data, then oftentimes, yeah, synthetic is not going to be of big use to you because you can just work with production data. However, there are instances where even then it can make sense to work with synthetic. And for example, in such cases like, I don't know, churn or maybe more like fraud cases, where you have highly imbalanced data sets. So for example, in fraud, maybe you have, I don't know, 1 million credit card transactions, but only 100 or whatever, 1,000 maybe are fraud, so very imbalanced data set. And that oftentimes is difficult for models to pick up. What you can do is with synthetic, you can create a synthetic version and you can upsample using, for example, conditional generation, like we showed before, you can upsample the minority class, and then depending on the models you're using downstream, you can get a lift in performance. It's not a silver bullet. It's not going to always give you better results if you have highly sophisticated models in the first place. Probably not so much. But sometimes, especially, for example, in insurance, where you have quite simplistic models for regulatory purposes, they need to be able to explain exactly what the model does and those kind of things, you actually see an uplift when you work with rebalanced synthetic data. So even when privacy is then not kind of like the core challenge, you can get a benefit from synthetic data. In that churn case, it depends, right? I don't know if it's highly imbalanced or not. 5,000 rows of data is not that much, right? So there could be some models that could benefit from actually, upsampling to 10 or 50,000 rows of synthetic, And sometimes maybe, last comment on that, what we also see with customers, what they're doing is they're actually mixing synthetic and original data. So again, if privacy is not the core concern and you have access to the original data, but yeah, maybe you don't have enough. And maybe you, for some minority classes or some outliers, you actually want to mix in some synthetic data, and that can also then really lead to improved model performance. All right, we're still waiting here for the last model, the transaction model to complete. That's kind of like the largest table here in that data set. Yes, question?
Yeah, so generally what types of, what data types are supported for this? I assume like it would be numerical and categorical data that works best with this?
Yes, so numerical and categorical is certainly like and we see it here now in all those demos, right? It's like the go-to kind of data. We do support also date time fields. So if you have, for example, transactions that have a certain timestamp that is also modeled synthetically and the temporal patterns are being retained. We do support geolocation data. If you have latitude, longitude data, and what we also support is text. So if you have text in a structured format, right? So we're not talking about, I don't know, PDF documents or, book length text, but if you have like, I don't know, tweets, for example, or if you have, I don't know, question answer pairs, text in a data frame somewhere, that is also supported.
What about like JSON, for example, the stringify?
JSON is not supported out of the box. You would probably need to do some pre-processing, post-processing to make that work.
Okay, and geospatial is like mainly the latitude, longitude, not like the like geometry.
Yeah, geolocation is only latitude, longitude. That's the only element there. Yeah.
Okay.
Yeah. Question.
When I run this cell, I get some deprecation warnings, or do you get them as well?
I did get them. Yeah, I did get them, and I still have them. Yeah, it's something I forwarded to the team. They could probably look at it. It still works, but yeah, we have those warnings. But yeah, this is now completed. We have now basically a generator that is representing those 7 tables from the Berka dataset, and we can now use that to generate synthetic data. So basically, as we did before, we just say, okay, mostly generate. In this case, we're creating the same amount of data, sample size here, but yeah, we could create more or less data as well here using that. And then once we have that as an output, of course, you could, I don't know, put this into relational DB. You could just, download this as CSVs or Parquets or whatever you want to work with. What we're going to do is here now quickly then afterwards, we're going to check for referential integrity. So are really the primary foreign key relationships intact? Because, of course, that's something that you want in such a multi-table setup. And then we're also going to look a little bit at some of the correlations actually across tables. Are they being retained or not? But yeah, first the data needs to be created. That will take probably another minute or so. On Google Colab, this will take, I think it took like almost 9 minutes or so. So like the full end-to-end flow took almost 30 minutes. So it is a little longer. It's still relatively small data. I think the transaction table has about 1 million rows. So it's starting to get a little bit larger. But of course, it's not, it's not terabytes of data. And typically, I mean, especially if you run in local mode, you can go to the millions. You can maybe go to hundreds of megabytes, maybe gigabytes of data. But yeah, this is not in local mode. Probably not going to run with terabytes or more. Yeah, we also get a warning here, but that's fine. It still works. We see here, we had about 985,000 transactions that were created. let's check the referential integrity. So it's now checking here basically the foreign and primary key relationships, and yes, 100% valid. All of these are valid, which is good. But yeah, we also want more. We just don't only want referential integrity, but we also want correlation, right? Information across tables. And so what we're going to do here is we're going to plot transactions per account by card ownership. So actually using information of 3 different tables. And what we see here, the transactions per account, this is the original data, this is the synthetic data, in principle was learned very, very well, right? So kind of like anywhere between between 0 and 600, kind of like this curve, it's learned. But we do in the real data see here a little bit of difference between card ownership, has card or no card. It seems like people that don't have a card tend to have a little bit more transactions per account. And we don't really see that in the synthetic data. And that's an example where, yeah, the model can learn a lot of the correlations also across tables, but there are certain limitations. Under the hood, there's something that we have implemented. It's called a sequential context processor. And it's trying to put as much context as possible into the learning process, but there are certain limitations. And again, if the table structure gets super complex, you have, I don't know, some self-referencing tables and those kind of things, it will not always work. It's trying to, yes, first of all, keep referential integrity, and then second of all, keep as much correlation, as much as information as possible, but there will be limitations. And here another one, looking at loan prevalence by card ownership. Yeah, we also see here now a difference. So the information between having a card or not having a card is not fully learned in all the other tables. Good, and then lastly, fair synthetic data. So I mentioned it before in the beginning already. You can also use our SDK to correct for biases in data. So again, let's load the US Census adult income dataset. By now we definitely know that. And I already mentioned, right, there's this one variable here, income, that says if someone earns more or less than $50,000 a year. And like it or not, back then, and probably still today, females are making less money than males, right? So this is an example of a biased data set. It's just the way the reality was back then. The question now, of course, is, okay, if I know this, is this something I want to accept? And okay, fine, right? If I build a income prediction model, for example, then fine, it's going to always predict that males make more money than females. Or is this something that I want to actually address and maybe correct for? And so this is what we're going to do. We will train now, again, a generator. And actually, in the training step here, there's nothing I need to configure. This is like we did before. In this case, I'm limiting the training time to 1 minute, but otherwise it's just standard. The fairness constraint is going to come then in the piece when we generate the synthetic data, kind of like in the second step, right? But a generator that has been trained, I can use, and then I can start thinking about fairness. When we talk about fairness, maybe a quick detour here. It is a somewhat complex topic because there is what is fair, right? There are different definitions of what is fair. And we have a little bit of a fairness blog series on that. We have here this blog post around impact of biases in data and then how synthetic data can help with that. Of course, there are other mitigation techniques for biases, right? And we also go into those here. I would say the beauty of it with synthetic data is it's quite easy to do. And we'll see that now in a second. All right, so the generator has been trained, and now we're going to create basically 2 synthetic data sets. One is a data set without any fairness restrictions, right? So like we did before, we just generate basically now the same amount of data. And here, and that's also important to remember, so the standard setting is the synthetic data is created as closely as possible to the real data. So any defects the original data has, they will be there in the synthetic data. And of course, if there's a bias in the original data, there will be a bias in the synthetic data, if you know about it or not. Again, this is not a bug, it's a feature, right? Because you want to recreate the original data as closely as possible. However, again, if I know about this bias and actually want to do something about it, I can do it. And so this is then the configuration here for fairness. Using the fairness parameter, I need to define two things, the target column and the sensitive column. So we're using a concept called statistical parity. It's one of the fairness definitions. Probably it's not perfect. There are others out there, but you will see it has an impact. And so what we're saying is we actually want to use the, this income variable, right? The prediction if someone makes more or less than 50,000. This is what we want to make fair. And we want to make this fair. We want to equalize this, the outcome, based on the gender, the sex column, right? So it should be independent if someone is male or female. They should make the same, the prediction should be the same amount of money that they're making. And there are others, right? You could look at the age variable, you could look at the, I don't know, zip codes where people live and all of those things. You could also actually have multiple columns that you want to correct for if you feel or if you know that these have an impact on the data. But in this case, we're just using the gender one. And so now we're going to just visualize this and compare this. And so what do we see? We see here the probability of someone making more than 50,000. Blue is the original data. And so we see, yes, males have a probability of, what is it here, 30 something %, whereas females only had a probability of about 10%, right? So less than half likelihood of making more than 50K. In the standard synthetic data, that is almost the same, right? So it's 26% versus 9%. If I had trained longer, it probably would have been identical, like 30 and 10. However, in the fair synthetic data, we see this is now dramatically changed because now the likelihood of a male making more than 50K is 21.9%, and for females it's 21.8%. Right? So we corrected this biased data set specifically on the gender, on the sex column. Everything else that was still in there in terms of biases, maybe age, maybe zip codes, maybe other things, work class, it's still going to be there, right? So if I want to use fairness, it is powerful, but I need to know what I'm doing, right? So I need to know about the biases that I have in my data set. I need to know about the variables that I want to correct for, but then I can do it. So, but it's not like, okay, just push a button and say, okay, make this data set fair. That's not going to work. All right, and that actually concludes the fourth example. So a quick recap, what we saw today. We started off with a kind of like, yeah, very easy, the core capabilities, just reading in a data frame, creating a generator, synthesizing that, creating a synthetic data set, and also then displaying here the quality report, also exporting that generator. We looked into differential privacy, if we want to have strong mathematical privacy guarantees. Again, the upside is, yes, mathematical guarantee. The downside is data quality gets worse and you have longer training times. So use it as you see fit. We then looked at conditional generation, right? So if I want to fix certain elements of the data set, and if I want to maybe simulate a different world, a different outcome, I can do that by providing this, what we call the seeded data frame, where the fixed variable is there. Or this could also be multiple variables. And then we looked at multi-table synthesis, relational DBs, more than one table, how we can retain referential integrity across those tables, and how we can also keep information and correlation across those tables. But we also saw, okay, the limitations, not everything is always learned perfectly. And then lastly, we talked about fair synthetic data. If I have data that contains biases, what can I do about that? And yes, happy to answer any questions that there might be.
Is there some relation between the fairness synthetic data and conditional generation? Can you?
Yeah.
It sounds similar somehow.
It's a very good question. So you could, for example, just say, okay, I want to fix the, and we did that, right? I want to fix the gender variable, and then what does it mean for the income? So there's something to it. The statistical parity concept around fairness is mathematically defined, and the way it's then sort of implemented in the SDK will give you exactly that, what the mathematical definition for statistical parity does. It is more complex than just rebalancing or conditional generation. So if you really want to remove biases, you you're better off using the fairness configuration because with pure rebalancing, it's not going to be as good. There are things like indirect biases that you will then miss and those kind of things. Any other questions?
So far, if you have any more questions, you can place them here or in the Q&A. Otherwise, thank you, Tobias. Thank you for introducing this library. I will definitely use on healthcare data. And thank you for introducing these terms, which were, at least for me, quite difficult before this presentation. So thank you very much for that. If there are no more questions, then I think we should thank Tobias with a final applause, please.
Thank you.